Hi folks, welcome to our second video on logarithmic functions. After today, you should be able to state the inverse of a logarithmic function, and we want to be able to graph a logarithmic function. So hopefully we should be able to do that after our lesson today. Okay, so for our intro here to get going on inverses, let's take a look at a kind of weird notation here. We're going to look at what is the logarithm base b of b to the x. Well, let's take a look at what this says. Let's change the form a second here. I'm going to take my base b to what power gives me b to the x. So I'm going to write it like this. B to the what power equals b to the x. Well, if these exponents really, they need to be the same because their bases are the same. So my question mark should equal x. Well, the question mark is this whole thing. So what this is telling me is that the log of b to the x, base b, is x. So what does this mean? Well, what this means is that logarithms and exponents are inverses. Because look at what we're doing here. I'm raising b to the x, and I'm asking what is the exponent that I raise b to get b to the x. And I know it's kind of almost like a little tongue twister there, but just believe me when I say that logarithms and exponents are inverses of each other. Okay, so there's our little statement there that says what this means: logarithms and exponents are inverses of each other. Okay, so let's look at the second one then. So this is saying, I'm over here now, b to the log base b of x. Well, it looks kind of weird, but look at what we have here. We have b to the, right? And we're asking, what is the exponent base b? Well, I have exponentiation and I have logarithm. Those undo each other and I get back x. Again, that's kind of a weird one. Let's take a look at another example here. I'm going to throw some numbers in. Let's say I do 3 to the log base 3 of 4. The key idea here is that the base in the log and the base in my exponent are the same thing. And I'll get back 4. Try this on your calculator. This one you can actually do on your calculator. Put that in your calculator. You should get back 4. Okay, let's look at a couple more examples. So these are 3 different examples. Let's take these one at a time. I'm at this first one here. We're going to evaluate the log of 10 to the 3x. Well, remember when there's no base written here, that's assumed that it's the common log, that's base 10. Well, again, notice how it's the same base as what I have in my exponent, or excuse me, as the base of my exponent here. So the log and the 10 to the are going to undo each other, and I should get back 3x. Okay, let's look at the second one. Well, these aren't quite the same. I have this 3, and I have this to the log of 81 base 3. We actually saw a way to do this previously in the last lesson. I'm actually going to take a different approach to this, and I'm going to write 81 as 3 to the 4. And now I can see that I'm taking 3 to the 4, right? And then I'm doing log base 3 of that. And I should get back what I started with, 4. Again, kind of a weird one there. Okay, let's look at one more here. Again, this is going the opposite way of the first two. This is doing the exponentiation first, and then I'm raising it to the natural log of 4. So again, the key idea here is that this is natural log. This is log base e, right? Okay, of 4. Okay, and I'm raising, excuse me, not 3, but e. Log base e. Okay, and again, the base that's here, this base right there, and the base that I have in my larger part of the problem here are the same thing. I'm going to get back my argument. I'm going to get back 4. Again, kind of a weird example there, kind of some weird example. But again, the main idea here is that logarithms and exponents are inverses of each other. I'm going to go back a page to where I said that before. And again, I'm just going to highlight this. This is a key idea here. When we get to solving equations, logarithmic and exponential equations, we're going to use the fact that they're inverses to help us unwrap. Okay, so let's find some inverses then. Okay, so first of all, notice that I have a logarithmic function, right? So what form should the inverse be? Well, we just said how that logs and exponents are inverses of each other, so we should end up with an exponential function for its inverse. So remember what we do to find an inverse. The first thing we do is we switch x and y. And then 2, we solve for y. Okay, so let's see what that does for us here. Well, I'm going to write this as x equals log of y base 7. And notice how I have that y is inside the log function, right? So I want to separate that out. So what we did was we do our base to our exponents equals the argument. So 7 to the x equals y. Or if I want to write that the other way around, I can write that as y equals 7 to the x. That's my inverse function. So again, this is this is an exponential function, and that's the inverse of log base 7 of x. Okay, let's look at one more example over here for finding an inverse. Same concept. I'm going to switch x and y. I'm going to solve for y. Okay, so I switch x and y, and now I'm going to solve for y. Okay, so, well, I need to know that down here, this is really base e, right? So I do e to the x equals y plus 1. And now I actually have a little bit of unwrapping to do here, right? I need to subtract out this 1 here. And I get e to the x, and then minus 1 equals y. That's my inverse. Okay, so admittedly, this is probably not the most interesting stuff. So what did we actually gain out of this? Well, I would argue that we gained at least 2 things. One, we get a little more fluency, a little more playing around with going from logarithmic to exponential form like we did really after we switched with the x and y. That's the first thing. And the second thing, we get a little more comfort with the fact that exponents and logarithms are inverses of each other. So now when I go ahead and look at the graph of these logarithmic functions, they should make a little more sense knowing what we know about exponential functions. Okay, so by the way, you're going to need some graph paper. Sorry, I didn't mention that earlier. But this is actually just going to be a pretty rudimentary graph, so you can really even just put this in with your notes here, along with just a couple of notes about what we're doing here. So we're going to make a quick sketch of, we're going to start with just a plain old log function, base 10. And we'll talk about the domain, the range, and we'll talk about the end behavior here. And then we'll look at a little more complicated function in B. Okay, so what I'm going to do here is I'm going to graph the inverse of y equals log base 10 of x. I'm going to graph the exponential function. So, and you can just take if you want to just take my word for this, the inverse of this log function here is going to be an exponential growth function that looks kind of like that. It's going to go through this special point here of 0, 1. In fact, there's even a second point that I know of. I know that 10 to the 1 is 10, so I have a point up here that's also on the graph of 1 comma 10. Okay, but that's a little off my graph, but I'm going to just throw it up there so that we see that the point is there. Okay, so remember how we find inverses graphically. We switch the x and the y, right? So this point here that is 0, 1 is going to be 1, 0 on the inverse. This point up here that is 1, 10, this one right there, is going to be 10, 1, and then it's going to be way out here somewhere. Okay. We also know that it's going to reflect across this line y equals x, this one that goes right on through the origin, right? It's going to act like a mirror. So I'm actually just going to draw this one by sight. I'm going to reflect this piece right here across the line, I'm going to get this piece. Oops, not very well done. I'm going to try that one more time. I'm going to get that piece right there. And I'm going to, this just continues, and it does not cross the x-axis here, right? So when I come down this way, I'm not going to cross the y-axis. And there's our nice reflection across that line, y equals x. Y equals x right there. So that's a visual way of getting the log function. So I'm actually going to get rid of my exponential now. I'm going to get rid of this stuff here. And notice this special point, this point right here, 1, 0, that's going to be on all log functions before we do any kind of transformation, right? So that point 1, 0 is going to be on every single graph. And the point 10, 1 is going to be on this particular one, but that's not our special point. That point of 1, 0 is our special point. One other thing that's worth mentioning is that our graph here on the right side, that's not an asymptote. That does keep going up. So this is not asymptotic, just to use a fancy word for you guys. So that does keep on going up and up and up, even though mine looks like it's kind of flat. Okay, so that's it. That's our basic log function. Notice how I don't get any negative values, right? There's nothing, no x values out here that actually get used. And we'll see why that is in a moment here. But for right now, I'm going to continue on to the next problem here. Okay, I'm going to go ahead and graph the y equals the natural log of x plus 3 and then minus 2. So I'm going to use our transformations here. So I'm going to start off by just thinking, okay, what does the natural log function look like? Well, it looks a lot like the common log function. It's just that the steepness of the line is going to be slightly different, but nothing that we really need to pick up on, nothing that I really need to show on my graph. So what I'm going to do is I'm actually just going to take my blue graph that's over here, this one, and I'm just going to copy it. I'm going to put the point 1, 0 on there, and I'm going to draw the curve going kind of like that. That's good enough. That'll definitely do. So that's my basic function. I haven't done any transformations yet with my natural log function, but that's what I'm going to do now. And notice here that we actually have, and I forgot to mention the first one here, we have a vertical asymptote right here. So I'm going to play around with that as well and when we shift this. So let's go through the transformations. Well, we have this plus 3 on the inside. Remember, inside is horizontal. It's the opposite of what it looks like. So this is going to go left 3. So I'm going to move everything to the left 3 units. So the first thing that's going to go is going to be this vertical asymptote is going to go. I'm going to move my point and my graph, apparently all as one, are also going to shift 3 units to the left. So that takes care of the plus 3. The next thing I'm going to take care of, and the last thing I need to do, is take care of this minus 2. Well, that minus 2 is outside the log function. That means it's vertical. That means it's as you see it. So everything's going to go which way? Everything's going to go down 2. Well, my vertical asymptote, I don't need to do anything with that, because going down 2 doesn't really do anything with a vertical asymptote. But everything else can go down 2. This whole graph, I'm going to grab the point and the whole graph, and I'm going to move it down 2. And I get a shape that looks like that. And again, the rest of the specifics, you need the shape of this log function. You should have the asymptote correct. And you should have this point right here, which ends up being at -2, -2, as it turns out. You should have that correct. So again, the specifics of any other points, like this one out here, I don't know that it actually goes through the point 2, -1. So I'm actually going to take that dot off. But the 1 point, the shape, and the vertical asymptote, those are really the important points of this graph. So we'll certainly play around more with these graphs in class. We're certainly not done with them. I know that these aren't the easiest things to get used to. So we'll continue to play around with these in the next couple days or so. Okay, so I suggest, or I posit that we cannot evaluate a logarithm of a negative number. We can't do it. In fact, if you look at the graph that we started with here, my original, I'm looking at this one right here. I don't have, remember how I said there's no negative values out here? So I can't take the log of a negative. Well, why not? Take a look at this equation right here. Log base 2 of -4, excuse me, equals x. Well, if I change this around, if I change this to exponential form, right, I'm just going to do that rather quickly. 2 to what power is going to give you negative 4? Is there anything you can think of that you can raise 2 to that gives us negative 4? Well, you might think that maybe negative 2 works, but remember, that's not how exponents work. 2 to the negative 2, that means reciprocal. That means a quarter. That doesn't give us negative 4. So that's our reason. That's our reason why we don't get negative values. And that's the reason why out here I don't have any negative x values being used on my graph. Notice how I do with my translated function. I do actually get values of between negative 3, excuse me, I should have put all those in there, between negative 3 and 0. I do get those values there, but that's because we added 3 inside the parent function before I took the log, right? So we can sometimes use them inside the argument, but we can't eventually take the log of a negative. Okay, let's look at one application problem and we'll call it a day. So this was this is part B to the application problem from the first lesson on logarithms with the slope of a sandy beach here. And again, we've already did this from last time. We did part A, right? We had this equation up here, right? Let me make this bigger for us here. We had that equation there for the slope of a sandy beach, and we had the diameter of the average diameter of sand particles, and we found the slope of the beach. It turned out to be rather shallow, right? Okay. So we're gonna use the graph. Now that we know what these graphs look like, we're gonna use the graph to help us estimate what the slope of the beach should be if what the average diameter of the pebbles will be if our slope is 0.2 in this case. So I'm going to go ahead and graph this. Yeah, I'm going to go ahead and graph this. You might want to get your calculator handy because I'm going to jump right to the y equals screen real fast here. Okay, so I put our equations in my y equals. So I have my original function here, right, and I have the width of the actual pebble. Excuse me, that's the slope of 0.2. So I've got those in there. I'm going to just do zoom 6, my standard viewing window, and see what this gives me. And as it turns out, it's really not giving me much. I can actually see when my two functions went, but really I don't have much here. So I need to play around with this window. So my first clue is that my y2 equals 0.2. So I need my y values, my y min, y max, to encompass 0.2. So I'm going to go from y min of, let's say, 0 to maybe 0.4 or 0.5. That should do it, right? I'm going to go up by tenths. And that way I know I'll get 0.2 in the window. It's a matter of, do I need to go out how far out on the x coordinates do I need to go? Well, let's just make life a little simpler. I know my x min is not going to be anything less than 0, because that would mean the width of the pebble is a negative value. That doesn't make any sense. I'm going to leave this as 10 and just see what this gives me. This might be enough. And sure enough, here's my log function. Here's my my slope of 0.2, and I can find my intersection pretty quickly that way. So I'm going to go second trace, choose number 5, and I should be able to just hit enter 3 times here. And I get a value of 2.226, which I now need to interpret. So this 2.226, so I get my input, or my d value was 2.226. That's the diameter of these sand particles, right, in millimeters. So each of these sand particles is going to be about 2.226 millimeters, which I guess that sounds kind of small. That could be reasonable for a diameter for some pebbles there. Okay, so in this last example, I would argue that while we really didn't learn anything new as far as how to use the calculator, how to solve problems, we did see what the log function looks like on the calculator. So hopefully you get a little more ease when you're looking at this thing, that you're going to be looking at a graph that looks, kind of like this, right? That's our basic log function right there. So hopefully you saw that. I'll bring the graph back up here a second. Hopefully you see that in this graph here, right? Here's our log function right there. Okay, so hopefully that was kind of helpful to see that on your calculator. Okay, so did we do the things that we said we're going to do? Are you able to state the inverse of a log function? And can you graph logarithmic functions? So hopefully this was helpful, and I look forward to seeing you guys next time in class. Have a great day.